very much for having me. I'm your field application engineer for the Bussmann division of Eaton. I cover the Northeast. So if you ever need anything, if you have any questions about this presentation, please feel free to ask during the presentation. Angela's going to be checking the chat. So please feel free to ask as we go through all of this. And my contact info is listed here. If you have any questions after the presentation is over, please feel free, give me a call or send me an email. So our agenda today, we're going to be talking about electrical hazards, right? So what are the electrical hazards? We'll do a quick overview of what they are. We're going to talk about the role of the overcurrent protective device during an electrical hazard. So, what that overcurrent protective device, what that fuse or breaker is doing and how it's protecting you. And then we're going to talk a little bit about arc flash mitigation. Some of this is required by NFPA 70E, and some of it is some additional safety that you might want to do on top of that minimum requirement provided to you. So first, we'll talk about, right, what are the hazards associated, right, with electricity? There's pretty much three of them: shock, arc flash, and arc blast. So the arc flash, that's the heat and fire part of an arcing event, and the arc blast, right, that's the pressure, shrapnel, and all that sound that comes from that pressure that comes out whenever you have an arc flash incident. So we'll first start very quickly about electric shock hazards, right? This one's pretty easy to understand, right? This is one we understand, like when we're children and our parents tell us not to put our fingers inside an electrical socket. But it's really a shock hazard is something that it's a source of injury, right, caused by contact or approach to energized conductors. So the amount of injury and the damage to your health depends on the current magnitude, so that amount of current that is actually there flowing through the body, and the voltage and the resistance of that current path also, play into that current magnitude. The current path, right? So exactly how is it flowing through the body? Does it flow through your heart? That's going to be worse than if it's not flowing through your heart. And then the amount of time that the current is flowing, right? Is it a millisecond? Is it 5 seconds? Obviously, the amount of time that it's flowing is going to make a big difference to the amount of injury and damage to your health that a shock can cause. So, how do we protect from shock? Shock boundary, right? Shock protection boundaries are the normal way that we see equipment listed, labeled in order to protect us from a shock hazard, right? So NFPA 70E, this is taken from table 130.4DA for AC systems. Right, you can see it. We've got a limited approach boundary, and the limited approach boundary is for qualified or unqualified people if they're accompanied by a qualified person. And then the restrict approach boundary is for the qualified persons only, right? So we have the restricted is slightly smaller than the limited approach boundary. And you can see, depending on what the voltage is, different minimum boundaries for any of those, depending on what your voltage range is. So under 50 volts, no limited approach value, but above that, various levels of limited and restricted approach boundaries. And this is typically how we protect, from shock hazards. The next thing, I really want to talk about is going to be an arc, right? Because we saw arc flash and arc blast, right? These are the ones that we typically kind of associate with NFPA 70E in general, how to protect ourselves from an arc flash event. So an electric arc, right? What is an arc? An arc is when electricity is being conducted through air, right? So a lot of times this occurs, maybe you have something very small that gets in between two conductors, and then that vaporizes, but the energy, that electricity, still continues to flow between them. and you've got that electricity flowing through air. That is your electric arc. That electric arc is insanely hot. 35,000 degrees Fahrenheit is the temperature of that electric arc. And as a result, you have radiant heat coming off of there. You have molten metal, right? And any conductors around there a lot of times start to melt or instantly vaporize. And so copper vapor, when it comes from a solid to a vapor, it expands rapidly, and that expansion rapidly, that's what causes that arc blast. There's also a lot of intense light, rapid hot air expansion. In addition to that copper vapor, there's hot air expanding. You get those pressure waves, sound waves, shrapnel. So lots of dangers associated with an electric arc. This is why we take so much time to make sure we protect ourselves from them, right? So here's my hazards, right? Heat obviously burns, and then the ignition of the material, and whatever else is around it might catch on fire, might become molten due to that very, very high heat. Temperatures you might want to remember as we go through this presentation, right? So a 2nd degree burn threshold, this is if it lasts for 0.1 seconds, is 80 degrees C or 175 degrees Fahrenheit. So that's a 2nd degree burn. 3rd degree burn, 205 degrees Fahrenheit. 96 degrees C to get that 3rd degree burn. You get intense light, right? So that could cause damage to your eyes. It could cause something like cataracts. You've got the pressures, right? Your eardrum rupture threshold is 720 pounds per square foot. So that's for your eardrum. And lung damage. So you can actually, when you get hit with a pressure blast that is strong enough, you can get lung damage from that. And you can see the range there, 1728 to 2160 pounds per square foot there. You've got shrapnel flying, right? That can cause obvious damage if that hits a person in the room. And just a pressure, if you are elevated during an arc flash or an arc blast, right, you could be flung across the room. You could be flung off of a ladder, a bucket, any other sort of platform you might be standing on. So lots of hazards associated with it. Again, this is why we take so much care to be sure we protect ourselves from them. So I want to talk a little bit about the role of the overcurrent protective device during an arc flash. So arc flash boundary and incident energy levels, right? So these are what we calculate. These are obviously proportional to that amount of energy that we see during an arc flash event. They are dependent, it is heavily dependent on 2 things: how long the arc fault lasts, right? So if you have a very, very short arc fault, not as much energy gets through. That's going to be dependent on the amount of time it takes that upstream overcurrent protector device to clear, right? How long until it opens? The faster it opens, the lower your arc flash incident energy is going to be. Of course, the time it takes to clear is related to the speed of that overcurrent protective device. It's also going to be dependent on the arc fault magnitude, right? The more current flowing through there, the more energy is flowing through there. So that's related to the available fault current. The available fault current is always going to be larger than the actual arc fault current. The arc fault current winds up typically being somewhere between 40 to 60% of your available fault current. But something like current limitation is going to be able to reduce the magnitude of the current flowing during an arc, and reducing the incident energy exposure levels as a result, right? So because it's the speed, how long the arc lasts, and then of course the magnitude of the arc while it's there, 2 biggest things that will be a determining factor in how much energy is released during an arc flash. So I'm going to show you a couple videos here of some tests that were done. These were done in 2000, in the year 2000, in the Cooper Bussmann, at the time, Cooper Bussmann facility, the Gabani Center outside of St. Louis. These tests were done. There was a safety committee. for some users, consultants, manufacturers, medical examiners, all there, to see these different staged arc flash tests. So our first test we did, so you could see here, you'll see this will always stay the same throughout all of these tests. 22.6 thousand available fault current. So that stayed the same the whole time. 480 volt three phase, that stayed the same the whole time. And what we have is we have a 640 amp non-current limiting 6-cycle short time delay overcurrent protector device. So this is basically a breaker. It would be like a low voltage power breaker that's often in something like the main in a switchboard, right? Or maybe a feeder in a large piece of switch gear, but it would be one of those long, bigger low voltage power breakers, the one that had intentional time delay, not the 30 cycle time delay that some of them have, the 6-cycle one that winds up being somewhere sort of in the middle of your power distribution system for coordination purposes. So the most common place again is this is a lot of times like the main in a larger switchboard would be this type of breaker, 640 amp non-current limiting 6 cycles. And then we put a fault on the line side of a downstream soup. So really it's right, it's going to be load side of that. So downstream of that breaker and upstream from the next. So the upstream overcurrent protector device, the one whose current limiting ability and time to open is going to matter, is the upstream one. That'll be that 640 amp device. So I'm going to go ahead and play this video so we can see what happens. So there's a sort of still frames of what you can see happened here. So, I got my mannequin here with his arm into the piece of equipment. And you could see that flash, right? Really, really bright light. I once actually witnessed this test in person, and I tried to record it on my phone, and it was too bright. It was just a flash of white all over my screen. That's basically what you're seeing in the second frame here. You can see some of the molten metal. Do you see that, those little sort of like sparkly pieces in there? That's the molten copper vapor in the air, and you can see that going right into that guy's face. More light, more light, smoke coming out. So there's a lot, even these still photos, right? You can see a lot of energy coming through here. So lot of light. You can see all the molten metal pieces. You could also see at a certain point once the blast, there's a very, very slight delay for the blast, but you can see the mannequin sort of kick back, his helmet flip back a little bit due to the blast. So here's my test results, right? So they had some sensors on this guy while he was standing here receiving this arc flash and arc blast. So the feeder did open in 6 cycles. So, I like to, 6 cycles, it is longer than sort of a typical molded case breaker, but that is what this type of breaker is designed to open in, right? So this breaker was opening the way it was designed to. Now my incident energy calculation here, 5.8 calories per centimeter squared at 18 inches. So we're going to, that doesn't necessarily mean a lot to us right now, but we'll be able to compare it to the later ones here. As you can see my sound level, 141.5 decibels. That's a lot. The pressure, right? We're at greater than 2160 pounds per square foot. That pressure, that 2160, that's the lung damage threshold, right? So there was enough pressure there that it could cause damage to the lungs. You can see temperature at the neck, which was just perfect, which was exposed. It actually pegged the meter, right? So it was more than 437 degrees Fahrenheit. My 3rd degree burn threshold, if we remember, was 205 degrees Fahrenheit. So I've got some 3rd degree burns most likely there. Underneath my t-shirt, that T3 was 122. So that actually was safe from 1st and 2nd degree burns under there. But my hands, which were, if you remember, reaching into that cabinet, also pegged the meter. So 3rd degree burns, on the hands there, if there's no proper PPE. So really, really high levels of energy. could cause some very, very severe injuries if you were in the path of that arc flash and arc blast. So our next test we're going to look at, again, this is the exact same available fault current and the same voltage. This time we have a 601 amp current limiting class L fuse in front of it, right? So, the same general amount of amps here. But we're going to use a current limiting class L fuse. And just by seeing the word current limiting here, we should expect this to be a smaller fault, right? Because we know at the very least that the incident energy is going to be proportional to the amount of current getting through. And if this says it's current limiting, it should let through less current than what the other one is. So we'll take a look and we'll see what happens in this test. All right, so some still frames here. You can see, right, there still is definitely an arc flash event occurring here. You can see that molten metal flying into his chest, flying into his face here. So it's still there. And you'll see the temperature readouts associated with it, right? But you'll see right here, right? The biggest thing here is that this opened in less than half a cycle. So not only was this device current limiting, so it reduced the actual amount of current coming through, but it also opened in that less than half a cycle. So it also reduced the amount of the duration of the arc, right? So by reducing both of those, right, my incident energy now is down to 1.6 calories per centimeter squared. It was 5.8 last time, right? So now you can kind of see, get an idea what each of those mean whenever we look at it. My sound levels, are smaller here. I can see T2, right? I'm at 143 degrees Fahrenheit. That's again at the neck where it's exposed, all skin exposed. That is under the 2nd degree burn threshold, right? So it was 3rd degree burn in the last one. This one, at least it's under that. The pressure, a lot smaller. No change in temperature underneath the t-shirt. Now the hand was reaching into that cabinet as close as it could be. It still saw high temperatures, right? That could still be a 3rd degree burn there on the hands if there's no additional PPE. But reduction, and everything you can see here on the right, basically, except for that hand. As far as the amount of health damage it could do to a person standing in front of it. The last one, and so this one is just really, really indicative. So we moved the fault in this case. So on this one, we moved the fault to be below a 30 amp RK1 current limiting fuse, right? So now the upstream device is something that's even smaller, and spoiler alert, it's even faster, right? And more current limiting than the 601 amp upstream fuse. So, we could see what happens to this arc fault. It's still the same available fault current, still 480 volts. But now the upstream overcurrent protective device is 30 amps instead of 600 amps. And let's go ahead and see what happens here. You just saw like a little flash there, right? There wasn't a whole heck of a lot. Couple little flashes, even with that hand right there. So if I see my results, right, no change at all in sound, temperature, pressure, even on that hand, which was, basically right there. So my branch overcurrent protective device, right, again, it opened in less than half a cycle, so it was really fast, but it was even more current limiting, right? So that made the bigger difference here. A 30 amp fuse is going to limit the current more than a 600 amp fuse. My incident energy levels also, listed there. So really this is less than 0.25 calories per centimeter squared, sort of the minimum threshold that you get when you calculate anything with the equations. So right, here's my comparison of the test results. So my non-current limiting device, so my arc flash boundary here, it's going to be 47 inches. That's pretty far away. It's 4 feet away. Before you are safe from this. Incident energy levels 5.8 calories per centimeter squared. Of course, that would also help you determine what level of PPE you would need to use. With the current limiting device, that arc flash boundary is cut in half. And my incident energy is right 1.6. So, you see incident energy levels. I feel like you see something like calories per centimeter squared, and you're just like, what is that? What does that number even mean? Hopefully, this helps give you an idea of what the difference between 5.8 and 1.6 is, and then really what essentially zero is. The test one's not zero, but it's the minimum levels that you can get, the differences in which those look like. Just again, trying to put some sort of concept in your mind as to what that calories per centimeter squared number really looks like in reality. There are incident energy tables for fuses. So if you are in the business of actually determining yourself what the incident energy and arc flash boundary levels are, for fuses, for any of the low peak Bussmann fuses, we just simply have a table. You can look up what your available fault current is. That's what's on the left, your bolted fault current. That's your available fault current. The amp of your fuse, and you get it right off of a table. So there's no special extra calculations required. The arc flash formulas can get a little complicated. There's some calculators out there for you, but very, very easy with fuses to just refer to this chart, look up the values, and have it. Really, really convenient if you are, again, sort of in the business of calculating that yourself, labeling your equipment yourself. Very, very convenient when you're using these Bussmann fuses. So with that, I'm going to talk a little bit about arc flash mitigation. This is where some of the new things in the NEC came about. So I want to talk about these on how we mitigate arc flash. And you can see from those videos why that is going to be a desirable thing to do, right? So this is in the 2020 NEC. There was a requirement added for arc energy reduction of fuses rated at 1200 amps or higher. Just so you know, there already is a standard for this for breakers, and that's been in the code probably at least 10 years, well, 12 years, for an arc energy reduction requirement for 1200 amp breakers or higher. In the 2020 NEC, they added this need to make it for 1200 amp fuses or higher. So, right, we're going to say we got to document that we have this arc energy reduction and your method. So this is where it gets a little bit more complicated than a breaker does. So what it's basically saying here is you need arc energy reduction if the fuse doesn't open during an arc fault in 0.07 seconds or less. So 0.07 seconds is the magic number. If the fuse at the arcing current opens in 0.07 seconds or less, you don't need any additional method to reduce the clearing time. If it opens in greater than 0.07 seconds during an arcing fault, you need to use one of these methods, like a differential relay, an arc reducing maintenance switch, or some sort of active arc flash mitigation system in order to reduce the arc energy reduction. So what that means for you, right, is the first thing you have to do is you have to figure out if that fuse opens in 0.07 seconds. And how do we do that? Well, you could do it the long way here, right? So in this example, we're going to take a 600 volt fuse. We're going to say it's a 1200 amp KTU. That's a Bussmann style class L fuse, 1200 amps. We know the available fault current, and then we take the lowest calculated arcing current. Again, this is something you could calculate yourself, or Bussmann even has a calculator available for that online. Figure out what that lowest calculated arcing current is. And you can see here, right, we've got that 0.07 line drawn across. So that's the opening time, right? So as long as this fuse, if I go to my lowest calculated arcing current, if I go on the bottom to 34.5 Ka, and I go up to my 1200 amp line, and if it crosses below 0.07 seconds, I'm good. I don't need anything additional. And in this case, that's what it does, right? In this particular example, we also, Bussmann released a very, very nice application note with this, and on it we provided a lot of the tables that you see here on the right. You've got your fuse, your amp rating, and then it'll tell you the minimum arcing current, right? So right here for KTU fuse, if I'm a 1200 amp fuse, if my arcing current is 11.02 kA or higher, right? So that's the minimum, I'm okay. I don't need anything additional. If it were lower than 11.02, that's when I would have to. It's interesting. Um, you would say, oh, obviously with arcing current, you want the lower values. The lower values are going to be less of a hazard, right? Well, that's not actually true with fuses. So with fuses, the lower the value is, the slower the fuse is going to open, right? The fuse opens faster the more current there is, and it opens slower the less current there is. So if the arcing current is actually sometimes too low, that's when you run into the need for this additional arc energy reduction. So high fault currents, higher voltage is actually a whole lot easier for a fuse to pass this test. It's lower arcing faults, lower voltages, where the fuses tend to need the added help. So this is one method, right? This is sort of like the long way, the hard way, always good for us to know how to do this. But the other really great news is that Bussmann has an amazing online tool that will just immediately tell you if a Bussmann fuse passes or fails. So arc.bussmann.com, that's the address you need to know. You put in the information that's up here on the top. So and even this gap between electrodes and the electrical configuration, right? You might look at that and be like, how am I supposed to know what any of that is? There's a really, really helpful note on either of those when you're on the actual website that'll tell you, oh, if you have this kind of switch, it's this or that or the other. So it'll help you determine, oh, if you're in a switchboard, your electrical configuration is this one. If you're in an MCC, it's this. So it'll help you decide what those top two are, because otherwise that's the hardest one to figure out. You know your voltage, you know your fault current, and you know your fuse amp rating. So you'll need those values. It'll give you your maximum and minimum arcing currents, and it will list every Bussmann type of 2000 amp fuse that we have, and it'll tell you if it passes or fails at that, right? So if you do this and you do this exact configuration as I have written here, and it passes, you're done. You don't need any additional arc energy reduction for this fuse. So this is clearly easier than the last one where you're looking at configuration charts or tables. You just input this information into an online web tool and you know whether or not you've passed or failed. This also does include a couple class T fuses that go up to 1200 amps, since this is a 1200 amp requirement and higher. So you might see some class T fuses in addition to class L fuses, but you'll know immediately. And not needing the additional arc energy reduction is always good. It means that you're going to probably save yourself some money if you don't have to put in any additional arc energy reduction. So with that, we'll talk a little bit about what that arc flash mitigation, how do you do this? How do you implement safety by design? So safety by design, this is part of NFPA 70E. It involves a hierarchy of risk control. And the first thing, right, is you always want to reduce the likelihood of exposure, right? So that's where elimination and substitution come into place. So that's number one. If you can just reduce the hazard completely, you do that. Engineering controls, right? That's things lockout, tag out, or really even like interlocks within pieces of equipment so that you can't get into them. Engineering controls is next. Awareness, administrative controls, right? That's, here's a maintenance procedure that you have to follow. And last is PPE. Always emphasize that last is PPE. You want to get that risk as low as you can. And then once it's as low as it can get, then you can rely on PPE. But you really don't want PPE to be number one on this list. You want to try to reduce the risk as much as you can with it. So current limitation, right? We already talked about this, is arc energy reduction, right? Current limitation is the same thing as arc energy reduction because arc incident energy levels are dependent on both the amount of time that arc uh, persists, as well as the magnitude of the current, right? So that first test that we saw, 6-cycle clearing, exactly the way that breaker was supposed to work, all of that right there's my 6 cycles, and all of the energy underneath of that curve gets through. The next test that we had, half cycle clearing time, and the other one was also less than a half cycle, quarter cycle clearing time, much smaller amounts of energy getting through there. So first easy way to reduce your arc energy levels is to use current limitation. You can use current limiting, we obviously, Bussmann, we love you to use current limiting fuses, but there are current limiting breakers out there available too. So there's various levels of current limitation based on your fuse type. One of the easiest ways to reduce arc hazards in your, and if you have something like an industrial facility, is to simply change the type of fuses that you have. So class RK5 fuses, those are the most common fuses. So the Bussmann sells more RK5 fuses than they sell any other type of fuses. So they're the most common fuse that's out there. They are also the least current limiting class fuse, right, at 600 amps and lower, at least. So if you see on this chart, you can see just but based on how quickly that it opens, and how much energy gets let through. Um, Simply changing an RK5 fuse to a class RK1 fuse will reduce your incident energy levels across the board. So the class RK1 fuse is more current limiting, and it also conveniently fits in the exact same holders and switches that the class RK5 does. So you don't have to change out any of your equipment. You just change out your fuses and you can get that reduced level. Class J is even more current limiting than either of the class R fuses, but it is smaller, will go in a different holder, so it would require some switching out of equipment if you have a class R holder, as it is. So, I always say class RK5, the least current limiting fuse, but I do like to emphasize that it's still more current limiting than any current limiting circuit breaker you'll see, right? A circuit breaker relies on a zero cross point in order to extinguish the arc. So at best, a current limiting circuit breaker can open at half a cycle. Most of them are at 1 cycle at the fastest, though. Current limiting fuses, by definition, have to open in a quarter of a cycle or less. So they'll always be faster and always be more current limiting, just as a result of that part of how they operate. So, like I said, sometimes the easiest way to achieve lower arc flash incident energy levels is to take whatever fuses that you have and upgrade them to a class RK1 dual element time delay fuse, a Bussmann low peak fuse. We call this a low peak fuse. The Bussmann low peak fuses are the yellow fuses. There's obviously lots of other different color fuses out there, but what's really great about these, again, it has to do with that ease of installation. So if you have any really old style renewable fuses out there, if you have class H or K5 fuses, those are non-current limiting, sort of older, very inexpensive types of fuses that are out there. If you have other class RK1s, other class RK5s of any manufacturer, because it's the beauty of fuses, right? You have the class and then they all fit in the same holder. The class RK1 will fit in all of the exact same holders and switches that any of the fuses listed on there have. It can also reduce your inventory, right? Because instead of having 4 or 5 different types of fuses, you now have one. So it's sort of it's a bonus. It reduces your inventory and decrease your arc flash incident energy levels. So that's one really great way, right? Just upgrade to the more current limiting style of fuse, easiest way to upgrade your arc flash incident energy levels. You can also specify, right now we're getting back here, finger safe. Finger safe, doesn't necessarily help you with arc flash, but it will help you with that arc, that that electric shock hazard, right? Finger safe products always very, very good for that. Um, the fusible panel board by Bussmann, if you've never seen this, this uses, this is a door-in-door style panel board, so it looks exactly like a breaker. There's a UL98, so it's a load break rated disconnect switch on each one of those branches with a Bussmann fuse inside. That fuse is current limiting, so you'll get all of the protection of a current limiting fuse there, and it's entirely finger safe. It's finger safe with or without fuses in the holders. So, you know, if you've got some spares that don't have any fuses in there, it's still finger safe. Um, I love this finger safe design of this particular product. So with this cube fuse, because it is finger safe without any additional covers, right? I'm sure we've all seen products, we've seen fuse holders that are finger safe, but there's a cover on them. And the first time you go to take the equipment out, you work on the equipment, you take the covers off, you put them in the bottom of the panel, you toss them, you lose them, and then it goes time to start the equipment back up and you don't reinstall those finger safe covers, right? So it's finger safe when it arrives at the facility, and then who knows what happens beyond that. So this is sort of inherently finger safe, right? In that there's no additional parts or pieces that you need in order to make it finger safe. Really, really great added value of this product. And again, more finger safe solutions. So there's that cube fuse solutions. You've got finger safe power distribution blocks. You can see those types of fuses that do have the covers. And again, the ones sort of the second to the from the left on the bottom, that one's nice because the cover is still attached, right? And something like that one on the third one on the bottom, right? That's a cover that you remove and you might toss and you might lose. But anything where that finger safe solution, it's inherently finger safe, doesn't rely on anyone replacing a cover when they're done working on it. Always a step up of one when it comes to a level of safety and minimizing your shock hazards. Barriers, also a great way to minimize your shock hazard, right? Add the barriers when particularly when you're replacing fuses. So there is a new requirement for line side barriers and service entrance equipment, right? So there should be line side barriers in your service entrance equipment. And this makes sense, right? If you turn off the main of your service entrance equipment, there's still live, you know, on the coming in there, right? There's still live conductors. So a barrier on that line side of your service entrance equipment really, really helps minimize the shock hazard. Dead front barriers are another example. Preventing that access to the live parts is really, really valuable too. Local disconnects are another really, really great way. You know, this is one of those ways where it simply just increases the likelihood that work will be performed in an electrically safe state. You know, how often is it that, you know, maybe an electrician goes out to work something and they just can't find the upstream switch to turn it off, right? If you can't find the way to turn it off, you are more likely to be able to risk working on something live when you shouldn't. So having a local disconnect right at the machinery, particularly a machine that would need, you know, likely need maintenance frequently, having a local disconnect there so that whoever the maintenance person that comes to work on it immediately knows where that upstream switch is, immediately is able to turn it off, and then therefore work in an electrically safe state is an excellent, excellent idea. We see this requirement, you can see here, right, for air conditioning units that are outside, you know, but there should be requirements, or they're not necessarily requirements, but it's a really, really good design philosophy for any type of machine or equipment that needs regular maintenance. Arc flash protecting overcurrent protected device. So another really good way to reduce your arc flash incident energy is to have a separate upstream enclosure, right? So when we talk about arc flash incident energy levels, it's always going to be dependent on what your upstream overcurrent protective device is. So it doesn't actually matter what's in that particular piece of equipment, right? That piece of equipment has an arc flash incident energy sticker on it. And that sticker is entirely dependent on what's upstream and has nothing to do with what's inside of it. So having a separate upstream enclosure, particularly one, right, that you could turn off, lock off in order to work on that downstream equipment, and having really, really good arc flash levels in that upstream enclosure is another really, really great sort of safety by design measure in order to reduce your arc flash incident energy. And then finally, an arc flash reduction maintenance switch. Now, these have been around for breakers for quite a while. You probably know it as an ARMS switch, right? Arc flash reduction maintenance switch, ARMS. And this, in breakers, this is integrated into the electronic trip unit. You have the ability, right? So the thing that this concept this works on is basically that most arc flash incidents occur during maintenance, especially the ones that are going to be the most harmful for maintenance workers, right? So what this will do is this will say, hey, we have this, very, very fancy electronic trip unit here. And what we'll be able to say is we'll be able to say, hey, I'm doing maintenance. So as soon as you see something, as soon as you electronic trip unit see something going on that it shouldn't be, know that I'm in maintenance and I've got a person to protect, and open as fast as you possibly can. Override whatever other controls you have, right? A lot of these fancy trip unit breakers, they have that purposeful six cycle delay, right? Like what we saw in that other one. And that's um, for coordination reasons, right? These are breakers that are higher up in your system, and you purposely want to wait for see if downstream devices will open instead of that, right? You don't want to cause a blackout for your entire facility, because of that one trip unit wasn't set correctly. However, if it comes down to blackout for a whole wing of your facility or kill the person working on the equipment, you're going to pick the blackout, right? So in this case, you're saying, I'm doing maintenance. There's a person I have to protect. You flip a specific switch, and now it says, okay, I've got a person to protect. And as soon as I start to see that current going up, I am not waiting like I normally would. I'm going to open as fast as I possibly can and protect, whoever is working on this equipment. And then when you're done doing maintenance, you just flip the switch back and you say, okay, you can go back to your normal settings, and not do that. So this is the arc flash reduction maintenance switch. This is always one of those acceptable methods of, arc flash reduction for the code for a breaker, or for a fuse. For the longest time, this didn't exist for fuses, and basically it didn't exist for fuses because there was no code requirement for it to exist for fuses. But now that there is arc energy reducing switches, basically the same thing, those ARMS switches exist for fuses. So, this is an example of the Eaton one. So this is not technically a Bussmann product, it's an Eaton product. Although you can get it through Bussmann. So it's a safety switch, right? So it's actually in the switch. And it's equipped with that energy reduction maintenance switch. So it's the same thing where it's going to say, override the normal trip curves that you have. Once I see 2.5 times the switch rating amount of current, I'm immediately going to shunt off. There's additional ground fault protection in there too, something you don't normally get with fuses, for this switch. So very, very cool product. It gives you that exact same thing that the ARMS switch on the breaker gives you, but with fusible protection. And this will help you meet that new requirement, that new NEC requirement for arc energy reduction at 1200 amps and higher of fuses. So very, very cool. And finally, the Eaton Bussmann arc flash relay, right? So you're allowed to use differential relay. This is another method of arc flash incident energy reduction. This is the best one, in my opinion, for existing equipment, right? So if you want to integrate arc flash reduction into existing equipment, this is the best way to do it. It's a little relay. It sits in on, this display sits in the front, out of your piece of equipment. where you have sensors within your equipment. It measures both light and current, right? So the reason it does that is right, sometimes you get spikes in current and it's not an arc flash, and sometimes you get light that's not an arc flash either, right? So it measures both of them. When it sees both, it'll know that you have an arc occurring, and it'll trip that upstream breaker. You can get a choice of fiber optic loop or wired point sensors. This is something I always include here because people who care about relay, they like one better than the other. And you can get it as either. So whichever one you prefer, it's available. But you can see here those light sensors, right? Those are installed all within the piece of equipment. All the way on the right, you can see the display on the outside of the piece of equipment. So you could see how this is really, really easily installed in existing equipment, right? It's just a couple pieces, this and a couple CTs that you install in existing equipment to be able to um, meet that arc flash reduction. Right, so what'll happen is you have an arc flash event occur, your line side CTs and your light sensor will see it. You've got this algorithm, right? It'll see it and it'll verify it's an arc event versus some sort of normal operation, right? So you don't get any sort of nuisance opening as a result of here. The Eaton arc flash relay will simultaneously send a signal to two places, right? You have your arc quenching device. So this actually moves the energy, right? So wherever that arc is coming, it'll work to contain it, move it away from where your maintenance worker might be, right? That's the commutate the arc. So it's going to try to redirect the energy coming and contain that arc energy and trip the upstream device, whether it's a breaker, it could be one of those, it could be a shunt trip fusible switch as well. And so it'll do both of those, and it'll do it a whole lot faster than that breaker or that upstream fused switch would do otherwise. So this is how that arc flash relay system would work for you. And finally, I'm just going to talk about a couple of maintenance considerations we want to consider as part of NFPA 70E. So NFPA 70E does tell us that the condition of maintenance, right, that's the state of the equipment, considering manufacturer's instructions, recommendations, applicable codes, standards, recommended practices, etc. So safety related maintenance requirements is covered, right? It's part of NFPA 70E. And it should be part of your overall safety plan because there is a direct relationship between maintaining your electrical equipment and safety. So there's, two types of your condition of maintenance, right? So the electrical safety program should consider the condition of maintenance of the equipment. Right? So if I'm the protecting overcurrent protective device, right, I have to consider the condition of maintenance of that, my upstream device, the one that is providing my arc flash mitigation, and the condition of maintenance of the downstream equipment, right? What is being protected, the equipment that's being serviced. So I have to the condition of both of these plays a very major role in the safety of my system. So some of your recommended maintenance requirements, right? So it should be maintained, right, in accordance with your manufacturer's instructions or industry consensus, right? And that reduces the risk associated with failure. And the equipment owner or owner's designated representative is responsible for the maintenance. So again, that's part of NFPA 70E. Your overcurrent protected devices shall be maintained according to your manufacturer's instructions. Maintenance, tests, inspections, all of these should be documented. So, you can see here, you can label the equipment. It was tested. Did it pass? Did it fail? Is it defective? Does it have limited service, etc.? Very, very important to know this about each of your pieces of equipment. Your overcurrent protective maintenance, right? The most important thing is that you want to maintain your overcurrent protected device so that it can adequately withstand or interrupt the available fault current, right? That's the standard that we're measuring them to. We want to make sure they can adequately withstand or interrupt. Fuses, So until a fuse opens, there's not a whole lot of maintenance usually associated with them. You want to make sure there's no breaks or cracks. Typically, it's the contacts of the fuses. So right, actually where the ferrules or the blades go into the switch, you want to make sure that the fuse holders, that's the most likely spot that'll need maintenance for fuses is that point of contact. Breakers maintained free of cracks, no broken operating handles. You are supposed to do testing after a circuit breaker opens after electrical fault. This is something that is right. It says, oh, do it per manufacturer's instructions. I know that this is something that is not regularly done in the field. It's very difficult because you'd say, well, how do you check? A lot of times it's checking for the cracks or the broken breaker people have told me one of the most obvious things is actually the way that it smells. Like a breaker that has interrupted too much fault current has this sort of like burnt-ish smell to it. So if you have a smelly breaker, you probably want to replace it, in addition to obviously looking for those cracks. But why do we care about maintenance? And it's mostly because the maintenance affects safety, right? Um, and an example here, right? Let's look at the left. This is my theoretical calculated values. This is piece of equipment is brand new and it's operating exactly the way it's supposed to. I have an 800 amp overcurrent protected device. It's going to open in 6 cycles. I've calculated my arcing current as a result. I've labeled all of my equipment. It tells me my incident energy level, 5.8 calories per centimeter squared, my arc flash boundary. When I go to work on this piece of equipment, I'm going to put on PPE that meets this level, right? I'm going to go with that boundary and assume that incident energy is correct. Put on right whatever my 5.8 calorie PPE might be. If I've poorly maintained this equipment, maybe that doesn't open in 6 cycles anymore. Maybe now opens in 30. Maybe it opens in 12, right? If it doesn't open in 6 cycles the way that I predicted, my incident energy is going to get higher. My arc flash boundary is going to get larger, right? So on the right, I have it saying, well, it's supposed to open in 6, but it actually opened in 30, right? Maybe I flipped a switch on there too, and I made it open in the wrong number of cycles. Whatever it is, due to poor maintenance, it now doesn't open as quickly as it does. Now my incidence is 29, but I'm wearing PPE for the 5.8, right? So you could see how you might have thought you did everything right. I have these calculated values. I have everything marked. I've got my PPE on. I'm okay. But if I poorly maintained a piece of equipment, and that incident energy isn't actually what it is anymore because that upstream overcurrent protected device doesn't open as quickly as it was supposed to, I could still be in trouble. So very, very important to maintain my overcurrent protective devices for this very reason, right? Your whole electrical safety program is based on these theoretical calculated values, and you want to make sure your actual values are at those same levels, maintain that same level of protection. The final maintenance thing I want to cover here has to do with the reclosing of circuits after the protective device operates. So you can see here highlighted in red, right? The repetitive manual reclosing of circuit breakers or re-energizing circuits through replaced fuses shall be prohibited. This is another one of those things that I'm sure happens very, very frequently in the field, right? So breaker trips, you say, oh, okay, I'll just reset it and it trips again immediately. You reset it again, trips again immediately. That is not a safe thing to do. You want to determine that it is actually safe to re-energize before you turn that circuit back on. This goes with fuses as well. Part of me, hey, I make more money the more fuses you buy. If you re-energize with the fuses, you'll just have to buy more fuses. But with a breaker, it's a whole lot easier to just go in and reset. You don't want to do the repetitive manual reclosing of those circuit breakers or re-energizing the circuits is prohibited per 70E. There's a similar requirement in OSHA. So very, very important we know that, right? When that occurs, it most likely means you have a short somewhere on your system. You really don't want to close an overcurrent protected device into a fault. They are not made to withstand something like that. They're supposed to be in a closed circuit, see a fault and open. They're not supposed to be closed into a circuit with a fault. So with that, just a quick summary, right? In my design phase to reduce electrical hazards, I want to use my engineering controls. I want to use a lot of those safety by design features. I want to specify current limiting overcurrent protective devices, right? Current limiting overcurrent protective devices are faster and they reduce that amount of energy coming through. They reduce the incident energy levels significantly. And I want to use touch safe products, right? That's to help me from the electrical shock hazard. For existing equipment, right? Don't work energized. That's usually the easiest one. Maintain your equipment, especially those overcurrent protective devices. Anytime you're putting on PPE based on a calculated level, you are relying on your upstream overcurrent protective device being maintained to work exactly the way it was supposed to when it's installed. So you're putting a lot of trust in that, so you want to maintain it to make sure it does operate that way. And then you want to replace any non-current limiting overcurrent protective devices with current limiting. You can utilize the low peak fuse upgrade program in order to upgrade those non-current limiting or less current limiting overcurrent protective devices to the one catalog number, lower your inventory for all of those. So some additional resources that you can use. The 2020 NEC code changes booklet. Bussmann publishes a code changes booklet every year. It's a fantastic booklet, and it includes all of this information that has changed in response to the arc reduction with fuses. We've got that online arcing current calculator and that arc reduction calculator. That was that arc.bussmann.com that can tell you, in a single click, whether or not a fuse that you have will pass or fail the new 2020 NEC requirement for fuse arc energy reduction. Got a data sheet for that arc flash relay. Again, one of the best methods to, I think, that there is to provide you that arc energy reduction in existing equipment. You could put it in new equipment too, but I think it's the best method that exists out there to retrofit existing equipment to come in line with this arc energy reduction requirement. Fault current calculator, right? You need to know your available fault current in order to know your arcing current, so that'll help as well. And then the SPD Electrical Protection Handbook has a whole lot of information on maintenance, electrical safe work practices, all within it. All of this is available on Bussmann's website, so you should be able to search any of these easily and find them. And with that, that's all that I have for this presentation today. If you have any questions, please let me know. And again, feel free to reach out to me after the presentation if you have more specific requests. But with that, I'll hand it back over to Angela.
Thank you so much, Chrissy. I really appreciate you providing all this information today. Following this conversation, the recording will be sent out to you all, as well as a survey. If you could provide feedback, that's really helpful for me and for Christy as well. And other than that, I'd like to say thank you for coming today. We'll stay on the line for maybe a minute or two more, just in case there are any questions.
Okay.
Okay, it looks like there's no lingering questions, so I'm going to stop.